All right. Hi, everyone. In this presentation, I'll present some of the experimental efforts we have been putting in realizing this protocol we call qubit-dyne, which is essentially digital homodyne or heterodyne detection of a stationary bosonic mode. This work has been performed at the 202Q lab at Chalmers. We are based in Sweden, so if you come up north, come say hi to us. It is done under the guidance of Professor Simone Gasperinetti. So, why use bosonic codes? I think this session needs no introduction for why bosonic codes, because they offer you encoding in a large Hilbert space with a single dominant error channel, with a clear hierarchy of errors, and also realizing hardware efficient error correction. To detect a bosonic state, there are a few numerous methods, namely Wigner tomography, which is based on parity measurement. You can also do tomography based on counting excitations. Or there is this protocol for tomography based on a holonomic gate, which lets you do it without a qubit. All this is good, and this is a non-exhaustive list, but it lacks one tool, which is homodyne or heterodyne detection of any of these stationary modes. Why would you want to have such a tool in your toolbox? Well, access to such a tool lets you perform efficient state verification. It also lets you implement multiple or multi-Gaussian operations if you are trying to do continuous variable measurement-based computation, or also implementing small algorithms like boson sampling and verification of it. This is not the first time someone is trying to do homodyne detection with superconducting circuits. It has been done on a propagating mode by measuring a generalized quadrature. But it was done by releasing the mode out of the cavity and then detecting it with a parametric amplifier. It reported an efficiency of 43%. But in our system, which is a 3D cavity coupled to a transmol, we have a typical 3D cavity setup, which is quite general to this audience now. What we want to show is with the qubit-dyne measurement procedure, which goes as follows. We take the 3D cavity, we perform a short entangling interaction of it with the qubit. Now we perform a rotation on the qubit and measure the outcome of the state. And now we reset the qubit. We'll come to why we want to reset the qubit. But now if you do this protocol a bunch of times and get this measurement records, x1, x2, x3, you can use this to make a weighted sum and get a homodyne measurement of this trajectory. Note that all this happens in one single lifetime of the bosonic mode. So this goes quite fast. There is a filter function we can estimate for each trajectory. And if you repeat this a bunch of times, you can collect a lot of these end trajectories, and these will reproduce what you get when you take a Wigner marginal of your bosonic state. Some of the experimental results. The protocol for such a the pulse sequence for such a protocol looks like this. In this case, we are using the G1 E0 swap to realize the entangling operations. This is not the only swap interaction you can use. This can be any beam splitting interaction. With the pi/2 rotations, the trajectory looks something like this. And now, to make sense of these trajectories, if you take a coherent state in vacuum, or just vacuum, the trajectories which you sum show a distribution as follows. But now, if you perform a displacement, you will see that along one of these quadratures, along which you have performed a displacement, you can measure a shifted distribution of the coherent state. Now, this might just be error in how you are collecting, but we don't stop there. We do sweep the angle of this displacement and try to see where our protocol lets us measure the coherent state is. And the circle here indicates that it does indeed follow how we are displacing the state and taking the measure of it. There is one issue we still are working on fixing, which is the origin of our protocol doesn't coincide with the IQ plane. But these were recorded just last week, so there's still a lot more work left to be done. We have also tried it for a Fock state, and there are some signatures that it works or shows a Wigner marginal, but we are working on fixing it. As an outlook and summary, the qubit-dyne protocol does unlock it's a good tool to have in the toolbox for studying the stationary cavity modes. We have seen signatures for small coherent states, and the outlook would be to look at them for large Wigner negative states. For example, if you are working with a Fock 3, the Wigner marginal should look something like this, and that is what we are aiming to measure. Thank you.
Okay, we've got plenty of time for questions if any one from the audience wants to ask.
Hi, thanks for the talk. Could you comment on the differences or advantages between this method and maybe a characteristic function tomography or a Wigner function tomography?
Yeah.
That's used.
So if you look at this map that I have or figure that I have, we do all this repeated blocks in one single lifetime, and these end trajectories that we are going to gather, it's just an averaging measurement of some sorts. So all this measurement data for one such distribution, we gather it in say 2 minutes of time. But if you now have to perform a Wigner tomography measurement, which we do in our lab, we see that getting a good Wigner plot typically takes an overnight measurement. And it's a very slow measurement because most of the time you're just waiting for the cavity to decay while you perform the parity measurement again at a different displacement. You can accelerate it by emptying a cavity fast, but then it's still a long time it takes to perform this measurement. So our protocol lets you do it a lot faster, and it can work for any unverified state preparation that you have performed. So then it's very easy to verify your state preparation as well.
Hi, thanks for the talk. I believe your group might have published a paper on using CVX for reconstruction of Wigner functions based on IQ measurements. Can you comment, or have you compared like fidelities using qubit-dyne versus the reconstruction method?
So far we have only done it for a very small coherent state, and if we do like a back of the envelope calculation, we see that this is about capturing 60% of the state. But since we have not performed qubit-dyne on any of the more complicated states, we have not yet gone that far to measure what sort of fidelities we get with the qubit-dyne protocol.
Okay, thank you.